So I accidentally stopped recording that for some reason. Okay. Was worried for a second. So now the next step is to encode apple into binary using this tree. So we've got, so you put zeros on the left branches, ones on the right. Okay, so 104A, P is 111, P is 111, L is 1101, and then E is 0. So that's typically what I'll do is I'll give you the reverse question, which is given a string, given this thing in binary, decode it. And if you come out with gibberish or you're left over with bits, you'll know that you did the initial part wrong. Just move on and come back to it later. Okay. So now let's go on to the coding portion of this. This isn't actually that bad at all. So write a method given a tree of integers, computes and returns the sum of all the integers stored in that tree. So rather than trying to brutalize myself, I'm going to do this in Notepad. So basically that there's essentially the same level of rigorousness that, essentially you guys will have. No syntax highlighting, no anything. So public static int sum tree node. And here we understand, because we're given a node with an integer, we know that this is going to contain, that the tree contains just integers. Okay. Write a method which, given a tree of integers, computes and returns all the integers stored in the tree. Remember, since this is going to be a recursive, so remember, when we're dealing with trees, it's going to be a recursive method, right? It's just the easiest way to deal with it. 90% of the time, it's going to be recursive. And I'll kind of and the last time is when you have to treat your trees as a graph. So in which case you don't use recursion. So public static sum tree. So we're going to just sum up all the integers in this tree. So remember, this could be a tree. When I say tree, this could be a tree or a subtree. So what if so we need a base case. So what's our base case? Yep. If root equals null, in which case what's the sum of all the integers in that tree? Yep. All right. Otherwise, now we know that. So now we know for a fact that our root isn't null. So we need to sum up all. So we need to sum up all the items in my tree. So that's going to be equal to what? The sum of all the items in the tree from a very high level perspective, because that's what you want to take when you're looking at it. It's kind of like an over obvious perspective. The sum of all the items in the tree, sum of all the left, sum of all the right, and sum of myself, right? So so int sum left is equal to sum tree root.left. Int sum right is equal to sum tree root.right. And now return sum left plus sum right plus root dot let's go with item or root dot number. I'll understand basically the thing inside there, or root dot data, whatever, right? But here, right, what if my left tree is null? Well, we'll get 0 back. What if my right tree is null? You'll get 0 back. Whatever. If your left tree has something, it will figure it out and get the answer back to you. And then you get the answer back to your parent or whoever called you. Remember, so these things are kind of ridiculously easy if you use recursion. I've yet to see somebody on the exam, I've seen one person on the exam not use recursion and get it right, and they used a stack. So, which amounts to the same thing, right? Because you use a stack to backtrack. Okay. So let's go ahead and look at the next problem. So this one's a bit more tough. This one's actually much tougher. Write a method which, given two trees or subtrees, returns whether or not the contents of the entire tree are identical. E.g., are tree A and tree B storing the exact same data in the exact same way? So a much tougher question would be, do both trees store the exact same data, right? But here we're asking, are both trees storing the data, the exact same data in the exact same way? Basically, do both trees have the same structure? So, for example, since I see plenty of confused looks, which I hope they wouldn't, because I give these practice exams out so you can look at them in advance. In other words, you've got 1, 2, 3 as A, and then 1, 2, 3 as B, right? These are the same tree, okay? But in my definition here, wait, that doesn't work, right? Because those aren't binary search trees, right? But whatever. So let's see. 2, 1, 3. There we go. And 2, 1, 3. Those are binaries, right? Those are equal binary search trees. Okay. But according to my definition, 1, 2, 3 is not equal because they don't, even though they hold the same data, they're not the same structure, right? So the key here to note is that if they were storing the data in exactly the same way, for two trees to be equal, that means that my roots have to be equal, right? That kind of goes without saying, right? And then my left tree and my right tree, they have to be equal according to the equals function, right? So calling equals on these two guys and equals on these two guys have to be the same, right? It has to return true for both of them. Does that make sense? Right? The only thing that's actually difficult is to actually hear the base case because you got to check for a lot of nulls, right? I mean, let me just get started with it because public static int. Sorry, no, this is a Boolean, equals node E. Actually, what did I say it was? Right. Technically, it should have been public static. I think it was an E here. Node E A. What did I call them? Did I call them tree A and tree B? Yeah. I'll just call them A and B for shortness here. Node E B. Right. First thing I have to do, if A equals null and B equals null, that's kind of a base case right there. If they're both null, well, then they're exactly the same tree in this case, right? So here I'll actually return true if they're both null. Okay. Then we just have a bunch of else ifs. Else if A is null and B is not equal to null. So in other words, if A is there but B is not, or so I'll actually just copy paste, but you could do an or there. Right, they're not equal in this case because one exists and the other does not exist, which means that they can't be the same by any sense of the definition. Another one over here, if on the other one and A is not equal to null and B is null, then again they're not the same. And finally, if they're both not null, which is the else, then we actually have to bother checking their contents, right? So first, if A dot equals B, right, you should use the dot equals method, but if you use double equals here, I'm not going to really count it against you here. If A is sorry, let's first check if they're not equal. That's actually easier. If the roots are not equal, if A and B are not equal to each other, right, then I can go ahead and return false and escape out of this madness. Right? But otherwise, I have to figure out, otherwise you know, I'm forced to do recursion at this point. So now I have to figure out, are my left trees equal? Are my right trees equal? And we'll see. So first, Boolean left result is equal to equals A dot left B dot left, and that will check my left and right tree, right? And then I just do the same thing for my right. And I'm not going to do anything fancy over here because I've already done enough damage, so to speak. Right result, and A is equal to, so now we check the right trees against each other. Left tree, right tree. So we've got, so now basically now we have to check, and now we return left tree, sorry, left result, and right result. So if they're both true, then we return true. But if my left tree happens to be different or my right tree happens to be different. And this looks a lot more complex, right? What's really making it complex is the fact you have to deal with two trees at once. But really, it's the same algorithm. First, I check my base cases, right? Which one of these things are pretty knowable, right? If they're both null, then they're equal. If one's null and the other's not, then, which is either of these cases, then they're not equal, so I return false. If they both happen to have stuff in them, well, check that stuff. If that stuff isn't equal, then I can just skip ahead and say they're not equal, return false. Otherwise, do this whole comparison on the left side, do this whole comparison on the right side, and if those both come back true, I'm going to return true. Otherwise, if either one of them is false or both of them are false, I'm going to return false. It's the same algorithm as above. It's just kind of disguised here. Does that make sense to everybody? All right, so this last one, this last programming problem, I am sorry I did it wrong. Write a method which returns write a method which returns which characters occur in a string and how many of each. Right? Which is a map, and I told you to get a map. And technically, this should have been, I don't know why I put an int here. This should have been like a string word or something, but that's what I get when I'm trying to write a new question when I have a bunch of children running around, and you know, my kid was playing with cousins, and I was busy trying to get this taken care of. So let's go ahead and copy this out and write this, because I think so. The only question really that will concern with the map will probably be worth 10 points. So string. And it'll be something along the lines of this. So here we're giving a count of all the characters that occur, all the characters that occurred in the string and how many times they occurred, right? So it tells you so usefully here, this problem actually tells you what you need, which is a character, right? So the key is the characters and the value is the integer. So what are the keys and values in this case, conceptually? Well, it's which character. So the keys are which characters that occur, and the value is how many of them. And here, if you're loose with syntax, that's fine, because I'm not particularly good with Java's syntax either. You just got to understand conceptually what is it. It's you really only have 3 methods though. You have put, get, and contains. So okay, so let's start. Map. You can, well, it's a test, so I'm not going to bother writing the generic. So map answer, or sorry, I'll call it, so maybe I'll call it map count is equal to new hash map, right? And I'll just go ahead and remember to return it here. Return count. Okay. So now, for every single character, so for there's a lot of ways to do this. You could do int I is equal to 0, then get the character at it. I'm just going to simply go for each character C in word dot to array, right, to turn it into an array. Or I think it's 2 character array. right? We'll turn the word into an array of characters so I can iterate through it like this. So now I'm just going through each character, right? But just write a for loop so you're going through each character. So for every character in the word, if count dot contains. So in other words, if my map already contains the character in it, that means I've already seen it in the character. Okay? So int times seen is equal to count dot get. Okay? Int dot, and so now, so that's how many times I've already seen it, and I've seen it one more time in addition to that. So now I'll replace it. Count dot put c and times seen plus 1. Okay? Else I haven't seen it yet. Right? If it doesn't contain it, I haven't seen it yet. In which case, what should I do? I should count.put C. I've seen the character, and I've seen it now once. And that's it. So it's, you know, if you try to do this with arrays or something, you're going to be in a world of hurt. But with maps, this becomes extremely easy to do. So yeah, that's not too bad. All right, so now let's go on to the. So actually, does everybody understand this? Okay. Right. So again, there's only really 3 methods you have to remember that exist when it comes to maps. Put, get, and contains. Right. And then you got to figure out what's conceptually going to be the key and what's the value. In other words, the keys are things that I am so typically the keys are either things that I am counting or categories. Okay? And the values are either counts or, you know, the things I'm categorizing. Okay? Analysis. How would a Huffman tree look if all the frequencies of the symbols were equal? So, in other words, if I gave you a problem like this, right? I give you a bunch of symbols and a bunch of frequencies. What would happen? What would that tree look like if I gave you a bunch of frequencies and they were all equal, like they were all 50? It would, yeah. It would be one. It would be essentially be on one level if you got a power of 2. If you got a power of 2, they would be on one level. But basically, they'd all be basically as equally far down into the tree. Which essentially means that actually that's kind of useless for a Huffman tree because they all appear at the same number of, they appear at the same frequency, right? These numbers appear at the same frequency. So, and the point of Huffman encoding is to give things like, less bits to the more frequent characters and more bits to the less frequent characters. And if they're equally frequent, then there's no point in doing Huffman encoding, right? Because when you've got it, what is the tree going to look like? You've got equal frequencies. Well, if you've got 4 characters, it's going to look like this. Internal node, 2 more internal nodes, and then character A, character B, and then character C, and then character D. Right? They all take 2 bits. Okay. And then if you've got another, side of that, that's going to be a 3rd bit. So it might be more efficient, but it's not necessarily the optimal solution here for compressing. So what is the average number of insertions and deletions? What is the average runtime of the insertion and deletion algorithms in a binary search tree and why? In other words, what's the average runtime for adding or removing items in a binary search tree? Log of n. Yeah, log n. And so why is that? Why is it log of n?
Because it's based off the depth of the tree.
Right. It's based off the depth of the tree. And what happens basically each step of the algorithm?
It doubles. Well, it's long.
Yeah. You do what at each level then? What happens to the number of choices you have?
Splits.
Yeah, it splits. It halves. Right. You're going one, or in using your depth context, you go one level deeper. Right. each step you're going one level deeper, right? Or as I like to put initially, basically we're looking at n items. Now I'm looking at, and then I go a step in, I'm looking at n over 2 items, right? And then I'm looking at n over 4 items, right? So I'm having the number of items I'm looking at each step, right? What's the worst case runtime for insertion and deletion algorithms? And I should mention we're assuming that these binary search trees don't balance. They don't self-balance. What's the worst case scenario? Yeah, O of n. Worst case scenario, you add 1, then you add 2, then you add 3, then you add 4, then you add 5, and your binary search tree stops looking like a binary search tree and more like a linked list. So so if you're trying to insert and remove in a linked list, it's O of n. All right, so we surprisingly made it through that in very quick time. All right. So questions so far? Sorry? No. God no. Those would be we haven't really covered self-balancing trees other than they take a rotation operation to do all that stuff. And B, that's more work for me. So, and it's already enough work to change my exam so that we put in hash tables. Generally, I put these in further. How are the timed labs going, by the way? So how many of you utterly hate and despise this lab? Timed labs, honest opinion. So I've got, so how many of you kind of hate it?
I hated the first.
Hated the first, okay. So kind of hate it. And how many of you are utterly ambivalent about this and will take whatever I throw at you? About half the class will take whatever I throw at you without complaining. It's good to know. And how many of you think this is the best thing since sliced bread? Nobody thinks.
Well, not best thing, but
You like that? Yeah, 1 or 2 people, because otherwise I'd be throwing more weight onto the exam. Is kind of the point, right? So that pairs up with my opinions in 1068, but 1068 only have an hour to do their timed labs because I've been, so they hate the timed labs, like with a passion. And the reason I'm doing timed labs this time around is because previous comments were, gosh, it would be great if the exams were worth slightly less, right? And so I'm like, okay, this is the only way I can make my exams slightly less because I already make my homework worth 35%, which is generally 10 points more than most professors do, right? Most professors do it 25% at most. I think I have it. Wait, do I have it at 25 or 35? 30%. Yeah, 30. So that's 5 more than most. So, okay. So I don't necessarily think I'm going to get anything else done today. So, I think you guys already have enough on your plate without subjecting you to another sorting algorithm. When we resume, we're going to cover more, the insertion sort. We're going to run through insertion sort briefly one more time, and then we're going to get into the quick sort and merge sort. Okay.